reference value derived from the voltage feedback. In this converter circuit, comparator is used to control PWM duty cycle using trip mechanism. Voltage reference is sampled through ADC and given as feedback through controller as input to the negative port of comparator with some slope compensation logic. For the positive port of comparator, the inductor current is used. If you can see the graph below, when the PWM is turned on, the inductor current increases, and when it reaches the reference level, the comparator switches off the PWM, resulting in decreasing in inductor current. Since inductor current is used in control logic, this method provides inherent short circuit protection, as the short circuit will drive inductor current to high and will turn off the PWM. Let us understand what is slope compensation and why do we need to do that in current control. In practical implementation, there will be some disturbances in inductor current which will cause subharmonic oscillations. These disturbances may be caused by difference between average inductor current and peak inductor current. Because of this variation, there will not be enough time for current to ramp down to original level if PWM duty cycle is more than 50%. As you can see the formula, the variation in inductor current keeps on increasing if duty cycle is greater than 0.5. Hence, this difference will keep on getting accumulated progressively over next cycles and may cause oscillations in output and cause unstable system. To solve this problem, instead of constant reference, a variable reference can be used. This reference will be a negative ramp, which results in elongation of inductor current decay time, especially if PWM duty cycle is greater than 50%. For best results, the slope of this reference ramp should be 50% of actual inductor current ramp. Using this, you can solve the equation to derive the actual ramp needed for a given reference voltage. Let us explore how we can model the DC to DC buck converter with peak current mode control. For this, we are considering the model based on TI kit called Boost XL buck converter. The main components we need to consider in this kit to model are switching and sampling circuits, comparator subsystems, and PI controller. Let us understand each of these components in more detail. This is a snippet of the schematic Boost XL buck converter. Here, I am highlighting three parts: MOSFET-based switching circuits, current feedback circuit, and voltage feedback circuit. We can consider each of these components and parts like resistors, capacitors, inductors, amplifiers, and FETs using Simscape electrical toolbox and model Simulink equivalent of the schematic needed for simulation of the buck converter. You can refer to the data sheets of the part numbers and find all the related parameters and use these values in the model. For PWM controller, you can see MOSFETs, capacitors, and resistors highlighted in the schematic or modeled in the Simulink using Simscape electrical. For current sensing circuit, the current we are looking for the feedback is the current flowing through the inductor L1. Again, here also you can see inductors, capacitors, and resistors highlighted in schematic or modeled in Simulink using Simscape electrical in the model snapshot below. In this scenario, you may have to add an additional gain introduced by ADC when used for sampling the current. For voltage feedback circuit, the voltage we are looking at for the feedback is the voltage across the resistor PR1. Again, here also you can see capacitors, resistors highlighted in schematic or modeled in Simulink using Simscape electrical in the model snapshot shown below. In this scenario, you may have to add additional gain introduced by ADC for sampling the voltage. One thing to note down here is the kit has additional provision to turn on and off the active load using the MOSFET switch Q1. This is also modeled in Simulink. Let us explore comparator subsystem and how we can model that. We can take the reference of the comparator from the actual comparator available in TI-2000 microcontroller. As you can see in the model, the SR flip-flop is used to switch the PWM on-off, and the comparator logic is simple comparison between reference and actual inductor current. The reference is generated from voltage feedback passing through the ramp generator to create the negative ramp reference. The ramp generator involves decrementing the value starting from max reference and resetting it back to the same value on every PWM period. The max reference and decrement amount is determined based on the slope of the ramp needed. As we saw earlier, the best results for the ramp reference must be half of the actual inductor current ramp. Expanding the formula, which we saw earlier, to convert the values from ampere per second to ADC counts per PWM cycle, The final formula will have additional parameters like T plant, 4095 corresponding to the ADC, 12-bit ADC we use in C2000 microcontroller, 3.3 volt reference, and GIFB. GIFB is basically the current gain feedback which we saw earlier. One thing to note down here is the slope calculation is very specific to the reference output voltage of the buck converter. If you change the reference voltage significantly, the RAM calculated may not work as efficiently as needed. All this component constitutes the plant model. We can use this part only to do simulation and cannot use it for the code generation purpose, as we must replace this with the actual hardware components for code gen and deployment. The PI controller is simple implementation involving the calculation of error between reference voltage and actual voltage. This error value is then used with KPKI gains and inductor feedback to derive the final reference needed for comparator. The reference used in the error calculation part is updated in small increments like 0.01. This constitutes a small and slow control loop for voltage, which is then used to calculate the reference needed for the fast current loop. The next step is to generate the code and deploy the model on hardware board. To do this, we have to modify the plant model and replace it with actual ADCs and PWMs from hardware board. For this, we are considering the TI F28379C launchpad. The following are the main components we'll look at more detail for the code gen model. EPWM and ADC configuration for switching and sampling circuits, comparator subsystem configuration, PA controller inside CLA, scheduling, additional logic for short circuit protection and debugging. There are multiple steps involved in PWM configuration to achieve the waveform what you are seeing in the graph. First, we need to set EPWM counter in up mode and set the frequency to 200 kHz. Then you need to set duty cycle to 100% using action qualifier and counter compare settings. Here we need to use trip 5 signal from comparator high to change the PWM duty cycle. For this, we have to use digital compare event 2 with blanking window to trigger the correct action qualifier. Then you need to configure the deadband to generate proper complementary waveform A and B. Then you need to configure one-shot trip action to trip EPWM to low when there is an overcurrent. Here we are using trip 4 signal from comparator low as a digital compare event 1. Finally, you need to configure the EPWM to trigger ADC startup conversion event. First, we configure the counting mode as up and configure PWM period as 499 clock cycles to generate 200 kHz PWM waveform. For EPWM action qualifier, we set actions needed to generate EPWM waveform. Here, we are setting the waveform continuously by setting counter is equal to 0 and doing nothing for any other action events to achieve 100% duty cycle. To configure the action qualifier using trip 5 of proper duty cycle, we are making use of custom code. For EPWM counter compare, we are setting compare register values to generate EPWM waveform. Here we are setting compare to 0, achieve 100% duty cycle, and proper duty cycle is achieved using trip 5 with custom code configuration. For compare B, we are using it to trigger a ADC startup conversion by setting this with 315 clock cycles so that ADC startup conversion is triggered before EPWM period event in every PWM cycle. For deadband, we are configuring to generate 15 clock cycles of deadband difference between normal and complementary waveform, and we are taking EPWM A as a reference for both normal and complementary wave. In the event trigger option, as I mentioned earlier, we are setting ADC startup conversion at counter is equal to compare B event in every PWM cycle. In trip zone settings, we are enabling one-shot trip action for digital compare event A1, where EPWM is forced to turn low. This is needed for overcurrent protection. We are configuring digital compare event A1 to set trip 4 event, which comes from comparator low. For this, as we saw earlier, we are doing one-shot trip to set the PWM to low. We are configuring digital compare event 2 for trip 5 coming from the comparator high. For this, we are applying a blanking window to filter out spurious events due to variations in current. We then use this digital compare event 2 to change the PWM duty cycle using custom code. Here we are using custom code to do additional configurations using system initialized block as we discussed earlier. The XPAR configurations which we are doing here is can be done in config set in 23A release. This model was created much earlier before the support of EPWM XPAR configurations from config set. That's why you can still see that we are doing this using custom code. Here we are linking EPWM trip 4 to compare low and EPWM trip 5 to compare high in EPWM XPAR. For trip 5 from compare high, we are setting action qualifier to set EPWM waveform to low, and we are also clearing all the existing trip events at the end of initialization sequence. Let us look at the settings needed for ADC sampling of output voltage. The ADC is configured with C module and is triggered through EPWM startup conversion event we have configured earlier. We are also triggering the ADC interrupt 1 once we have the data ready at the end of conversion. We are using two comparator modules, compare high and compare low. Compare high is configured to sample inductor current at one input port, and the second input will be an internal DAC with the ramp module to generate the negative ramp reference. The comparator will trigger compare event on EPWM and output XBars. We use this event from EPWM XBar to trigger trip 5 action for EPWM as we saw earlier. The comparator ramp will be reset based on EPWM synchronization event EPWM1 sync pulse at every PWM period. Compare low is configured to sample inductor current at one input port, and second input is a fixed reference which is basically the overcurrent limit. The comparator will trigger the compare event on EPWM and output XBars. We use the event from EPWM XBar to trigger trip 4 action for EPWM as we saw earlier. Here we are using some custom code logic in the same system initialized block as we saw earlier to set the proper analog source pins as input to the comparator. The comparator low DAC value is set with the initial value at the end of the init. These settings are currently not supported, and hence we are using custom code to see the values to set the values at the end or mid of the init functions. The PI controller remains same as we saw in earlier simulation model. We are configuring the control law accelerator to run PI control loop inside the CLA instead of CPU. The reason to do this is CLA runs parallel to CPU and can run math operations at faster rate, and we can run control loop efficiently at 200 kHz rate, while we can use CPU to run additional logic like logging signals or debugging using serial blocks. As we saw earlier, ADC is configured to trigger ADC1 interrupt 1 at the end of conversion. Here we are making use of hardware interrupt block to trigger ISR for ADC event. The ADC interrupt with CPU number 1 and pi number 3 is configured to run at high priority and non-preemptible. The entire control loop, including the comparator, will be run inside ADC ISR. So we are using ADC interrupt to effectively schedule the entire algorithm. You can also see the serial interrupt with CPU number 9 and pi number 1 configured to run serial receive routines needed for monitoring and logging signals. We will see more details about this in later slides. In 23A release, we have a new hardware interrupt block along with the one shown in the image. The new hardware interrupt block provides a drop-down option to do the interrupt configuration, and we do not have to remember CPU number or pi number to do this. There are additional event-based configuration options available in the new block. We are configuring serial receive block to read the data inside serial receive ISR. The serial baud rate is set at 6.25 MHz and configured to trigger interrupt when 10 bytes are received in FIFO. The receive block will output 5 word inside ISR, and then we can process these words to read and take appropriate parameter tuning action for the data received from the host model. We are configuring serial transmit block to send data needed for monitoring in the host model. The serial block is run inside do while loop to buffer the data over a period of time with proper header and terminator so that we can monitor the data in the host model at the speed at which we can perceive visually by our eye. This helps us not to miss out any data points when we are trying to send data at faster rates. This framing option is integrated as part of serial transmit block from 23A release, and no need to create additional for and do while loops. We have retained this for now in this model, example model, as this model was created in earlier release when this option was not present. This is the host model we use for serial data logging. We are using serial host configuration, receive and transmit blocks to receive and data, receive data from C2000 MCU and send data back to C2000 MCU. The receive block buffer size needs to be configured based on the loop size we set for serial transmit block in target model. The serial receive block is then routed to display the signals with the frame to sample conversion option set to visualize the C2000 microcontroller data in the scope. The parameter which needs to be tuned are sent to serial transmit block, which will be received inside ISR as we saw earlier. These parameters can be tuned and the effect of tuning can be watched on the scope in real time. We are using dashboard blocks to tune these parameters. When integrating the multiple subsystems together, we may have to share signals between subsystems running at different rates. To do this, we need to add rate transition blocks. For rate transition blocks, if we select data integrity option, we need to make sure that initial conditions are properly set. For example, if you are sending the signal for the overcurrent trip limit subsystem, if your initial conditions are incorrect, it may cause an incorrect PWM trip and algorithm may never run as it is a one-shot trip. In the example model, this value needs to be set to a value of 5 or more, as this is the value we want to monitor the overcurrent logic to trip PWM. The final step is to integrate the simulation and code gen model together so that we can iterate and finalize the algorithm in one single Simulink model. For this, we use the variants capability. From variants, we can make use of variant source block to source the signal for simulation and code gen based on the plant and hardware subsystem. We can keep the activation of variant during model update time. Similarly, we can also make use of variants subsystem to switch between different subsystems used for simulation and code gen. We can keep the activation of variant during model update time. Setting the model step time to proper value is important. This must be done carefully, especially when we are integrating simulation and code gen blocks together. As simulation models has planned subsystem which is running at 50 nanoseconds and code gen model is triggered asynchronously by interrupts. And the only step size what we see is 0.1 seconds needed for LED blink. If the step size is set to 50 nanoseconds for the model, the deployed algorithm may never run on hardware as the timer used to schedule the base rate in hardware will not be able to generate this step. The recommended approach is to use auto as the Simulink will select the proper rate needed between simulation and code gen. This is the final model with the simulation and code gen subsystem integrated in one single model. As you can see, each of the subsystems are running at different rate, like periodic rate and asynchronous rate. In periodic rate, you can see the plant models are running at 50 nanoseconds and 200 kilohertz rate. And the code gen models are running with the asynchronous rate triggered by hardware interrupts. Let us switch to the actual model, run simulation, deploy the same on hardware, and compare the simulation and actual results. This is the example model we will be looking at in order to understand how to do a simulation and how to watch the results when you deploy it on hardware. So this model has both simulation and code gen subsystems integrated together using variants as we discussed earlier. As you can see here that the model has sampled the lowest sample time of 50 nanoseconds, which is basically the sample time of the plant models. And 5 microsecond is a sample time of the simulation component corresponding to the PI control loop. The PI control loop for code gen will be an asynchronous subsystem. And similarly, we will see the serial receive is asynchronous subsystem in the code gen variant, but in simulation it will be a periodic rate. And there is an heartbeat LED which is running at 0.1 periodic sample time. So couple of things we have to ensure is the rate transition which is going in over current limit. I set it to 5.2 so that it doesn't trip with the 0 as an initial condition. And in terms of modeling, I am setting the fixed step size for the model as auto. The reason being that simulation code generates different sample times. Setting it auto ensures the model selects the proper sample time when we are doing different operations. So now let us look at the simulation and understand the results. I have already ran a simulation for this model. So the way to run simulation is to ensure we have set a proper stop time here and press this button to run the simulation. The stop time here is set at 0.05 because the smallest rate this model has is at 50 nanoseconds. So with 0.05 we are getting a huge number of samples, and a model will take some amount of time to finish this stop time. So in order to view the results of the simulation, I will click the data inspector. So in the data inspector, I have already logged the simulation. Let us look at some of the signals and understand how we can make use of these signals and understand how the model is working. So I'm looking at inductor current reference, which is basically a negative ramp, actual inductor current with respect to PWM waveform. As you can see, we see a lot of sample points here. So I will try to zoom in with respect to time in order to make more sense of this signal. As you can see here, the reference inductor current is a negative ramp, which is reset at every PWM period. And whenever PWM is turned on, the actual inductor current increases. And when it crosses the reference, PWM will be turned off and inductor current starts decreasing. So this is what we were trying to achieve using the comparator, and the simulation results shows this behavior accurately. Let us look at output voltage with respect to the reference voltage and see how it is coming up. So we can see that reference voltage was set at 2 volts and output voltage ramped up nicely and then settled at 2 volts. So this is we can probably run one more simulation quickly and try to understand how we can tune some of these values and see how the simulation results will vary. So let me quickly run this simulation button. While it is running, so let me try to vary the voltage request levels and active load switch also. Try to enable and disable the active load. So let me turn it off and turn it on, and let me change the active voltage request to 2.7 or around that value. And let us take a look at the data inspector and see how this variation is impacting. When I turned down that active load and turned it off, you can see there was some small variation of voltage level, and then it came back and settled nicely. And then since I requested the voltage at around 2.7 volts, the actual voltage, again changed 2.7 volts, and it is continuing in that path. So you can even vary the KPK gains and see whether your system is stable or any additional changes needs to be done. All those variations you can look at when simulation is running. So let me stop this simulation and let us look at how to understand and how to monitor the signals when you are running the model on hardware. As I mentioned earlier, I have already generated code and deployed the model on hardware. So this you can start the code generation and deployment by clicking this build, deploy and start button. So that generates code and it deploys to the 0049C hardware board. And once that is done, you will be able to open the host model and monitor the signals from the host model. So this is the host model which we'll be using to monitor the signal, and this is the scope I am monitoring. And for the host model, I have set the serial configuration COM port for serial configuration, serial receive and serial send blocks based on the COM port availability from the device manager. So in the device manager, the COM port is COM12 and I have set it accordingly. Now I am running the simulation. So this serial data will be reading the data from the target and it will be sending the data back to the target. And you can see that the voltage is at 2 volts as we are sending the request at 2 volts. Now let me vary the voltage request to a different value, let's say for probably 1.2 volts. And you can see that the actual voltage is reflected in real time. And let me turn the active load to on and off, and you can see there is small variation when I turn this active load switch on and off, and voltage is still maintained at a constant level what I have requested. So one thing to note here is the ramp we have calculated for the comparator's reference slope is basically with respect to the reference voltage of 2 volts. So the ramp will continue to work in a small range in and around 2 volts. But if you try to move beyond, the range, the range probably, more than 4 volts or less than 1 volts or something, the system behavior may not be as expected. You may have to recalculate the RAM with respect to that reference voltage. So as you can see, now I have set the reference voltage to 2.4 volts and the actual voltage is also at 2.4 volts. So this is real-time data we are reading from the 0049C hardware board. I will stop the simulation for now. That's all from my side. Thank you for listening. Over to you, Jay.
Thanks for the details and demo, Aditya. To wrap up, I just have 2 points. First one is that you can use Simulink and Simscape for modeling and simulation of power conversion algorithms of your power converters. Then you can model the embedded application to run those algorithms on the TI-C2000 microcontrollers using the hardware peripheral blocks from the C2000 microcontroller block set. Thank you for your time. Now we can take questions. Hello everyone. Thanks to Aditya. I think we have few questions here. So the first one is, can you show the SCA communication blocks, how that is happening?
Yeah, so let me share my screen. I will probably just walk through the model, which has the serial communication and configuration. Let me know if you can see this.
Aditya, your audio is low.
Can you see my screen?
Yes.
Okay. Yeah. As I mentioned earlier, so we need to have a serial blocks both in a target and host. So when you are in the target, you have this driver blocks for the serial receive and serial transmit, where we configure how much of data you want to read. Right now, we are running the serial receive blocks inside a serial receive ISR, as I mentioned earlier. So I'm setting the sample time as -1 with the header and terminator. And I have a serial block, which is basically
the serial transmit, and this one we use it to send the data to the host machine. So both this will serial blocks will be running on the target, and we have the serial configuration basically to set the baud rate, select the pin which is connected to the UART to USB, and we have configured the serial receive FIFO interrupt to trigger the interrupt when the data level is 10, which means 8 bytes of data when 10 bytes of data when we receive, it will trigger an interrupt. And in the host model, so I am setting the same baud rate. I am selecting the COM port based on the COM port of availability in the device manager. So serial receive, I am setting the COM port like a header and terminator, and the data size of whatever the data I am receiving. Right. So while sending, I was sending it in a while loop, as I mentioned, with the counter value of from 0 to 1200. So receiving, I am receiving that much size data with the sample time of 0.06, considering the rate at which we are running the serial transmit. And here I'm sending data, 5 data points, 5 unit 16 translates to 10 units, and header and terminator. So this communication happens through COM port from the target to host, and that's why we are able to see the data.
The next question is, can you show the generated code?
Yes, so yeah, okay. So this is the main code, and this is our step 31 step. This is triggered by the timer 0. So timer 0 we configure it for the base rate, and we step at that base rate. And this is our main code, which is running in a continuous while loop. And if you see, this is where our the algorithm and everything goes in. So this is our ISR code. This is our step function, which has the base rate functions, whatever that is running. This is our initialization function. So we have enough comments which indicates clearly so which subsystem generated which piece of code. So this is the initialization code containing ADC, PWM comparator. This is our EDC one interrupt ISR, and this is our serial interrupt.
The next
And
question,
then we have some additional initialization routines for ADCs, interrupts, and PWMs. And this is our CLA code. And this is coming from here. Yeah.
yeah. And the next question that we have is, how is the slider for KP and KI being taken and being changed during the hardware synchronized setup? So the host communication model
Mhm. So
to
there are two slider things, right? These are the sliders. So this you can use it when you are doing simulation, because simulation we are doing only one model. But on that, when the target is running and the host model, you want to change these values. So you have KPKI gains. So when you are running this host model, you will be able to change this value, and these values, these sliders are linked to this constant flux. So you should be able to, if you see here, this is linked to the P gain, and this slider is linked to the I gain. So whenever we change the sliders, these values will be sent uh, through serial send to the target, and here we are receiving in serial receive all the data points, and then we use those data points as part of running. the routines for code gen and things. So sorry, only the code gen. So if you can see, these KPK gains are coming from there, from the serial receive.
Okay, I'll take up the next question. So, what is the main difference between embedded coder support package for TIC 2000 and the C2000 microcontroller block set? So, until MATLAB release 2022B, we had the support package, and now from 2023A, we have C2000 microcontroller block set. There is a wide list of features difference between these two. We have something called connected I/O, which we have recently introduced in the C2000 microcontroller block set when it has transitioned into a product, and also some additional C2000 device support like the latest process 15X and 13X and all are supported in the C2000 microcontroller block set. We have also added some CLA math libraries which you can use, uh, which is a feature provided by the C2000 devices to do some math operations using the C2000 MCU itself to reduce load on the CPU doing such math operations. Anything else, Aditya, you want to add? To and few more examples that are available in the C2000 block set, which contains simulation model. Say, for example, this one, what you are seeing right now in the demo, the support package did not have a simulation model for the buck converter. So it was just a code gen model which was there as part of the support package. Aditya, you want to add something for this question?
No, nothing else from this side. So other than that, typically, the block set, we are ramping up with the new processors. In 23B, we added T800 and 0015. So yeah, that is going to be the continuous process. So yeah, other than that, nothing else.
The next question is, are there ways to optimize the generated code to run faster?
Yeah, there are a couple of things you can do in order to optimize the generated code. You know, one is right in the hardware settings, in the optimization, in the code generation time. So there are additional steps you can do. So here in optimization, you can select different set of options here in order to optimize what you want. And in the code generation also, here you can mention very specific set of things, right? If you can add compiler optimization flags like O2, which runs the code faster. Other than that, you can do some additional settings to configure the subsystems to run in a RAM. When copy the entire subsystem from flash to RAM and run from RAM, which will enables to run faster. And more such settings are possible. Like for example, you can make use of CRL code replacement libraries as part of the C2000, and in hardware implementation, you can enable some hardware accelerators like TLU. So these are some of the optimization routines you can enable, and you can generate the optimized code.
How do we partition algorithm to run inside CLA and CPU?
So one thing from the partitioning, right? So what we do provide is like we provide CLA task and CLA subsystem are the two options, two blocks we provide as part of our C2000 library. So this CLA subsystem is basically the pre-configured subsystem which has all the required configurations to run and to place the code and data as part of CLA RAM. And only thing what you have to do is once you have the subsystem, you may have to uh, set the inputs specifically for running from CLA RAM. So CLA task you can either trigger from software or any other trigger options. There are certain limitations with the TLA, especially because TI uses a different tool chain to compile CLA, but ultimately generate the same set of uh, single executable for both C2X and CLA. So because of this, there are certain limitations, like you will not be able to use certain things inside CLA. And we have a page where we explain how to use CLA, what all additional things you can do. So that's a very good page. We explain all the things you can do and what are limitations and uh, how to go solve those limitations and implement the algorithm inside CLA. So this is one point reference where you can figure out everything. So there is an alternate way of implementation or using the CLA, where you use a model reference with the CLA task trigger block, and that comes with the system on chip modeling workflow. So there are certain limitations there, as in like it is completely supporting multi-core processors like 37X and 38X, and single core processors. There are certain features not completely supported there. But overall, I think these are the things you can use and leverage to partition the algorithms to run inside CLA.
The next question is what is base rate and multiple sample times being shown here? How does that affect code gen?
So the thing is, typically when you are configuring the model, you need to understand what is the base rate at which you are running. So right now, there are two components as part of this model. One is the simulation and there is a code gen. The simulation, if you, as you can see, right, so the entire control loop I am running at 200 kilohertz or 5 microseconds. So for that, in order to simulate it properly, I need the plant model to be simulated at least 100 times faster. So the sample time for simulation is much higher. And when you are coming back to the code generation, you can see that uh, the most of the code gen is triggered through asynchronous through hardware interrupt or serial interrupt, right? And DPWM, as we saw earlier, we are configuring PWM to run at 200K, and EPWM is triggering analog to digital converter, and ADC is triggering an end of conversion at the end of sampling. So ultimately, the ADC interrupt is triggering at the 20 kilohertz, the rate at which PWM period is running. So the entire code generation is running asynchronously, as you can see here, while the simulation is running at 200 kilohertz. And when you are setting up different sample times, you have to set up the rate transition accordingly. So for the code generation, what we make use of is timer 0 to uh, configure the base rate. So the base rate right now, the periodic rate is 0.1 and 0.01. These are only two base rates because rest of them is running asynchronously. So timer 0 is configuring the base rate and triggering the periodic task, while asynchronous tasks are triggered by users.
And the next question is how to handle noise in ADC.
So the noise in ADC, right? So if you can see, there is some specific set of configuration for ADC where you can increase the acquisition window or increase the acquisition windows. Basically, you can think about that the time is needed for the capacitors to charge and hold the sample value. So that itself is like a filter, and but on top of it, you can implement additional filtering mechanisms, like you can implement a IR filter which filters this ADC, and you use that filtered value as a how to run the PI controller. So there are ways you can even increase the sampling of ADCs, oversample the ADC, and then use a window-based filtering, and then use that filtered data to run the controller also. So you can do those kind of mechanisms as well. So out of ADC, you can use an IR filter depending upon what kind of noise you want to filter.
The next question is, how do you make sure that the algorithm does not overrun?
So there is a configurable option in hardware where we target hardware resources where we enable uh, overhead detection. This provides additional option to set, clear or toggle GPIO depending on which GPIO you want, and then additional options like trigger interrupt or call your own function basically to you know take some evasive action or give some kind of notification for you to understand whether the algorithm is overrunning. So once if we find it is overrunning, do some additional settings, like do some additional things like investigation, figure out which one is causing taking more time, try out the optimization methods, profile individually one by one and figure out which one you can make it more efficient, and other things you can try.
The next question is, how do you configure the hardware interrupt?
So there are two hardware interrupt blocks are available as part of the block set. So one is the hardware interrupt you saw as part of the slide, wherein you can just figure out what is the CPU number and pi number for this interrupts and corresponding set there. For example, I want to trigger an interrupt for ADCA1. So the CPU number and pi number is 1. And you see this CPU number is set or pi number is like instead of 3 is 1. In this case, I am setting pi number as 3, which is basically for ADCC1. And similarly, if you see line 1 corresponds to serial interrupt. And then you set the simulation task priority and preemption. So the task priority is basically to ensure which one is higher and which one is a lower priority. And preemption is to ensure whether you want that to be preempted or by a high priority task or not preempted. So priority is an inversion priority. So the base rate is at 40. And in the 23A release, we have the new, along with this hardware interrupt, we have new hardware interrupt block also, which is easy to configure in terms of selection. On the block, you can see number of interrupts and ceiling task priority settings, and then you can open the hardware mapping and pick up whichever interrupt you want and select which event you want to trigger an interrupt and configure the same. You can see the serial like ADC interrupts are configured with any ones. Output of this is basically the function for subsystem. It's basically used to trigger the ISR routine. So this entire thing will go inside an ISR.
Okay. The next question that we have is, do you have motor control examples with C2000? I'll take this. So yes, we do have motor control examples. Aditya can show some examples which are available. These are available in the C2000 microcontroller block section. They use the booster packs that TI provides and the TI's motor control kits to have these examples. Yes, we don't have any more questions. You can type in your questions in the Q&A.
So there is a question how to get offset data in the basic class. I think you can use if you want to filter the offsets, you can use the disable filter for now. Right, when you are sampling out of EDC, you have to analyze and see what kind of signals are you getting, and then you may have to implement the filter. Right now in our algorithm, we have not implemented any additional filtering as part of the signals. But you can see in some of the motor control examples, the output of EDC is filtered and used in the control.
Yeah, if there are no more questions, maybe we can wrap up. We have 1 more minute left until the scheduled time. If you have any questions, just type it in the chat or in the Q&A. Yes, we have the last question. Can we get the recording of the session later? Yes, it will be sent to you in after 5 days. And it will also be available on the MATLAB website. You can watch the recording of the webinar. Okay then. Thank you everyone for your time. We'll wrap up the session.